So that's a bit of a summary of what we have seen so far. So we considered a scalar field with some mass m, and then we were considering the very high temperature region where the temperature is much bigger than the mass. Then we saw that in the perturbation series there are diagrams which give large corrections if the mass is very small. And a new scale appeared here, this so-called thermal mass, which is, so the thermal mass squared was of order lambda t squared. So the thermal mass has a square root of lambda times t. And we are doing perturbation theory, so we should at least formally assume that this is small. So that means that this thermal mass here is still much less than the temperature. So we have this hierarchy here. And then, yeah, we computed things. We got this from the ideal gas limit. There are no interactions included here. And then the first correction was from a two-loop diagram, which is this here. And then the third one came from summing an infinite set of diagrams, which were all these daisy diagrams with arbitrarily many of these petals here, where inside the loop the Matsubara frequency is 0, and outside we had this hard thermal loops proportional to t squared, which gives rise to this thermal mass. And yeah, since the mass dependent from the zero frequency contribution, the mass dependent term is m cubed, then this term here becomes thermal mass cubed, which gives us this funny power of lambda 3/2, which is specific for hot gauge theory, field theories with bosons. I mean, this is an effect which only appears with bosons, because for fermions you would never have zero frequency here. Okay, this is the structure that you get, and now you could move on and do, for example, gauge theories like quantum electrodynamics at high temperature or QCD at high temperature. And interestingly, the structure of these three terms here is exactly the same. So you start with ideal gas, and then you get a kind of normal looking, without resummation, you get a correction of this type. And now for gauge theory, say for QCD, for example, you get similar, same structure with lambda replaced by g squared. G strong squared, if you want. Right? This is the strong coupling squared. And why is it squared? Because you see this came from this diagram here. And in case of QCD, that comes from this 4-gluon vertex, which is proportional to g squared. And also there you get a thermal mass, and then you get in that case, a g cubed contribution. Yeah, one could say a lot more about this, and maybe I will say a lot more about this at the end of the lecture, maybe tomorrow if I have time left. But now I would like to move on to the second part of my lecture, which is about real-time correlation functions. So far we only talked about thermal equilibrium and say the pressure, equilibrium properties. We could, well, not just compute the pressure, we could also compute like fluctuations of certain quantities. And but it was all, so to say, without any time dependence. So now I would like to discuss real-time correlations. And this will allow us to treat also systems which are not quite in thermal equilibrium. They're close to equilibrium in a certain sense, but we can have deviations from equilibrium. So far, remember we discussed the propagator of the scalar field. So this is an expression of this type where you have some operator at imaginary time t and x, and some, say operator 1 and some other operator 2 at, say, time 0 and space point 0. This was an imaginary time actually we had to consider here this imaginary time ordering TE. That we can compute using this, our imaginary time formalism. Now, this is obviously not a physical time, so this doesn't represent something we can directly observe, except if tau is 0 here. Then we have an equal time correlation function which could describe fluctuations that we could measure. But for non-zero tau, this is not directly physical. So what is physical is could be observable is if we replace this here by a real time. And this is what I mean by real time correlation functions. And one can again define this. I mean, we know what this is. This is so this by this I mean is thermal expectation value. So this is 1 over z times trace of e to the minus beta h of this whatever is in here. So we could as well, instead of this expression, we could as well put a product of operators at different real times. So this would give us something like, so we may also define and say O1 at T1 and x, it's t and x, times O2 at 0 with real t. Yeah. And what we will see is that all these type of functions can be obtained from the imaginary time ones. So our formalism will still be useful, and these type of functions will all be related by analytic continuation to these here. But before I discuss that, I would like to show you a physics example where this type of correlation function appears. Okay? So this describes, as I said, describes this properties of systems close to equilibrium. Now, let me give an example what a situation like this could be. Example, it's particle production or production of very weakly interacting particles. So one popular example is, for example, the production of photons in a quark-gluon plasma. So what people do, they collide heavy ions and then they create some kind of matter of quarks and gluons, which is very complicated and you have many interactions. But the quarks in there, they can emit photons. And the photons only feel electromagnetic interaction, which is much weaker. So in most cases, these photons just escape the system and can be observed. So that is such a situation, and we can use such functions here to compute the rate at which these very weakly interacting particles are produced. So let me be concrete. Instead of photons, I consider a scalar particle, the so-called axion, which is a pseudoscalar, which could be the dark matter. Or what I show is also valid for what people call axion-like particles. So axion-like particles is just some general, light pseudoscalar. Consider production of axions or axion-like particles in the early universe. Suppose you have none of these, or practically none of these particles in your system, then there are reactions, and at some point there will be one of these axions will be created, and then so the phase space density, so let F be the axion phase space density, which if they were in equilibrium, it would be just Bose-Einstein, but we are far from equilibrium, so we start, say, with F equal to 0, and then at least at early times, then we would have an equation like this, that the time derivative of the, say, has momentum k, time derivative of F at momentum k is given by some production rate gamma k. Okay, so how, and now so to say, the task is to compute this gamma k. So for that we need to know how the axions interact with the plasma. So we write in interaction Lagrangian, where we have the axion field A, and that couples to, so this is a pseudoscalar, this couples to a pseudoscalar operator, and well, what one always has for axions is the coupling to gluons, but I will consider here, for simplicity, I will consider coupling axions to photons. So I have here a pseudoscalar, which I just call rho, made of electromagnetic fields. So by rho I mean that is electromagnetic coupling, fine structure constant over 8 pi times the electromagnetic field strength tensor times its dual, which is, in terms of electric and magnetic field, it's alpha of over 4 pi times E dot B. So the axion couples to this density. So you have lots of photons flying around, and with this vertex here, with this interaction here, you get, you can produce axions which corresponds to such a vertex. So here you have two photons, and they can make an axion. Okay, and then we still need here some coupling constant, which describes the strength of the interaction. You see, this is a scalar field, so it has mass dimension 1. This has E dot B, that has mass dimension 4, so it's total mass dimension 4. So this must be dimensionless, this has a negative mass dimension. So it is 1 over some energy scale, and typically this is a very large energy scale here, which appears here. Okay, now how do we go from this interaction to get the production rate? Well, we imagine finite box with volume V, and then we start with a state where we have no axions at all. Then we let the system evolve, and then even if the interaction is very small, at some point you will make one axion. And then we consider what is the probability to find one axion in the system at time t, at some later time t. So that is this probability p. So p is probability to find one axion with momentum, say k, at time t, if there was none at time 0. Okay, so P is equal to, that's the usual expression. We have some initial state I, which has no axion. Then we run the time evolution to time t, and I use the interaction picture, which with respect to this interaction here. So that takes us from time 0 to time t, and then we take the scalar product with a state f, which again has all kinds of, say, standard model particles but no axions, plus a single axion with the momentum k. So let me write it like this. And this is the amplitude here, and to get the probability, we take the square of that. Okay? Now, what is the time evolution operator? That's, you can expand. I mean, we assume that this interaction is very weak, so we expand our time evolution operator. So if the first term is, of course, 1, and then the first correction comes from a single power of the interaction here, so that is minus I times now the integral from 0 to t dt prime of the interaction Hamiltonian, and then it goes on with higher powers of this interaction here. And what we assume is that we have only a single interaction, so we just stop here. So we replace this by just the first term here. That is, of course, only valid if we don't wait too long, because if we wait too long, the axion we can make more axions, or one axion is destroyed or whatnot. That we don't want. So we want only one single interaction. So this expansion will only be valid for t not too big. Let's call it t much less than some interaction time, which can be very long if this coupling here is very small. Okay, now we plug this into this expression, and the first term gives 0, because here you have no axion, here you have 1, the orthogonal gives 0. The first term is, so let me write the amplitude, fk u times I, that starts with the first order and this. Well, let me first write this here. Okay, let me first say something how we treat the axion field. Sorry. So I said we use the interaction picture where the field operators satisfy the free field equations, so we can write our axion field at space-time point x as a, well, remember I consider a finite volume, so then momenta are discrete. So I have here sum over momenta, and then I normalize it such that I have here 1 over square root of volume, and then we have the usual expression for scalar field operators. We have an operator which annihilate, where we have a solution with positive energy, so minus I p dot x, and then there's a annihilation operator for axions with momentum p, and then there's the Hermitian conjugate, which is e to the I p dot x times the creation operator of an axion. I think you cannot see this. Let's see. Maybe I should. Now you can see, but I should write it underneath. So that's, yeah, that's fine. Yeah. So this funny normalization is such that the commutator of a creation operator and an annihilation operator C P C K dagger is equal to 1 if they are equal, and 0 otherwise. So that is delta P K. Okay, that's my. That's how I write the axion field, and now I can use this to compute the amplitude. So I have f k time evolution starting from initial time. Then we get the Hamiltonian is minus the Lagrangian, so we get, instead of a minus I, this is the Lagrangian, and which is minus the Hamiltonian, so instead of, if I write the Lagrangian, I have a plus I here. Then I get a kappa, a coupling constant, and that I can pull out. What else can I pull out? I can pull out the integral over time from 0 to t dt prime, then integral over all space, because the Hamiltonian is the integral over Hamiltonian density. Yeah, now comes the matrix element. So F, so this, the K I get by applying a creation operator to a state without axion, and if it acts to the left, it is a CK here. That makes this, it turns this here into this. And then I have my axion field at x prime, and then I have my what I called rho of x prime. Okay. Now here, if I have an A dagger here, if I have a C dagger in my axion field, and if that C dagger acts on F, I get 0, because there is no axion here anymore, and the A dagger acting to the left would like to annihilate an axion. So the only contribution here comes from the commutator term of C with a C dagger from the axion field operator. So what I get is a that takes away the sum up there, and I get here 1 over the square root of 2 times energy for K. So I forgot to say what is EK. or EP. EP is in yesterday I defined this. There I said it's p squared, the square root of p squared plus m squared. But now we assume that the axion is really light, so we just neglect the axion mass and right here this is just the size of the momentum. Okay, then here I have this, and these integrals. Then we get from the so we use this operator here to plug it into the commutator, so we get an exponential from here, e to the I px, and p is now k, so it's k dot x prime, and then inside the expectation or the matrix element there's only a row left. Okay, that's our amplitude for any states I and f. Now I square this thing, and when I square, so if I square this object f ui, I get all these factors here, but then I also get a the matrix element here, f ui I, and times its row of say x2, and then I have a complex conjugate of one of these, that is then I row of x1 times f. Right, this is the structure I get. And now I want to compute the total rate, so I don't really care what f is, so I sum over all the f's. And what this does, if I have a complete set of states f and I sum over all of them, this turns into a unit operator. So this here turns into 1. And for the initial state, I want to assume that I was in thermal equilibrium, that, I mean, everything but the axion was in thermal equilibrium. So what I should do is I should do the thermal average over I. So meaning that I sum over I with a e to the minus beta energy of the total. I mean, this is not a one particle energy, but the energy of the whole system. Okay, what do I get? Let's try to collect all the factors. Absolute value squared, so I get p is a kappa squared. Then I have 2 of these square roots, so it's 1 over 2 times e k times the volume. And then lots of integrals. 0 to t dt prime, say dt1, integral 0 to t dt2, integral d3x1, integral d3x2. Then we had this exponential here, and we have now 2 exponentials. Let me write them like this. And then we have here, what else? Exponential, and then we have, so this turned into 1, and if I take thermal average here, this leaves just the thermal expectation value of a product of two of these densities here, rho of x1, rho of x2. Yeah, and now we see we already there. Remember, before I just erased that, I said we can express that in terms of unequal time, real unequal time correlation functions, and here we have precisely this type of function. Yeah. Okay, now we can of course simplify this expression still. So this, once again, we can assume translational invariance. It's the same, of course, in the beginning I talked about expanding universe, and that is all should be, at the end of the day, when we can compute really the axion densities, we should take this into account. That would mean that but that just means that I modify the left-hand side of this equation. I mean, this will not change our gamma k. So for the computation of gamma k, we can just assume a static box, provided the expansion is slow enough so the standard model particles stay in equilibrium. So this here is, by translational invariance, is the same as rho of, say, 0 times rho of x2 minus x1. How did I do that here? No, I had x2 here, sorry. So x1 minus x2. And this type of function is also called a Whiteman function, or which is written like this. So it's called delta less of, and is a function of x1 minus x2. And I write here rho, meaning that it's the Whiteman function of two rho operators. Okay, now you can do, you can shift the spatial integration variables. Then we shift x1 by x1 plus x2. Then we only have a x1 here. Then there's no x2 anymore left inside the integrand, and this gives us a total volume, which cancels this factor here. There's only a single spatial integral left. And now comes a trick, which also takes away one of these integrals here, is that we consider not the probability, but the time derivative here, dp dt, that takes away either this or this integration. And if you do that, I mean, it's a now straightforward integration. You have to differentiate this two, and then you get two terms, and you can combine them, and I can just write the result. So I should actually here put the brackets around this, because this is the not the probability, but the thermal average already. So write it like this, and what you get is, so it's the kappa squared over 2e, and then the integral over space, or integral over time, over space, and integral over time, and the time goes, as said, there are two contributions, one from 0 to t and one from minus t to 0, so that can be combined to this integral here. Then we have e to the I k dot x, and the Whiteman function of rho. Okay, now if you look at this integral here, then suppose this would be from minus infinity to plus infinity. This would just be the Fourier transform of the Whiteman function. Okay, but it's over a finite interval, and now comes a important point. We assume that the axion interacts very weakly, so for a long time nothing happens. At the same time, the standard model particles interact all the time. They interact a lot. So that means that if you have some fluctuate, I mean, in equilibrium the E dot B is 0. So if the rho is non-zero, it describes some thermal fluctuation around equilibrium. And if you, after a certain time, then if you had a fluctuation in this direction, then it will still be, there will be non-zero correlation with that at a later time. But if you wait long enough, then this correlation will go away. And this thing here goes to 0 if the time difference is too big. And the time scale for that is related to the time scale of the standard model interaction rates. So, but if this time t here is much bigger, then we have this here can be practically 0. So this here is practically 0 for t prime, say much greater than t, how did I call that? Correlation time. Say t correlation time means the correlation of these operators. So, and now if we assume that we can find a time which is in between this interaction time and the correlation time, or we can choose may choose t somewhere in between this interaction time of the axion, which I said is arbitrarily slow, and the correlation time of the standard model, which is not that slow, then we can ignore the fact that this is only a finite interval, and we can just take it from minus infinity to plus infinity. And then this here would just be the Fourier transform of the Weidmann function.
The superscript in Weidmann function. Hello? The superscript. Is that related to some causality or something? So that this is on mic, right? So the superscript in Weidmann function greater than.
Yeah. I mean, I will show in a moment.
This is related to causality or something, because I assume your interaction Lagrangian had time reversal symmetry, right? The L int that you wrote has time reversal symmetry, right?
Has what?
Time reversal symmetry, right?
That
if you inverse the time, it should stay.
I mean, it's in both these operators. I mean, I have A of t and x.
So I assume, my question is, why do you want to consider retarded? So I did not understand, why do you want to just consider retarded? You can have also an advanced thing.
The translation invert.
Oh, it's not anything related to retarded?
It's just Weidmann, but there are two Weidmanns where you put 0 first and x second and x.
There are more explanations required.
Okay.
So the factor of v should also be there, right? In the last expression.
The factor of
1 over 2 EV. The d average p dt. The next one. Yeah, this one. There's a v also there, or the volume v.
I mean, that goes away from this integral here.
Oh, okay.
You see, I mean, I shift. So what I can do here is in the integration, I shift x1 goes to x1 plus x2. Then the x2 disappears from this function, and it disappears
Okay.
from this function. And then it's just the integral over all volume, all space.
Okay.
Yeah? Okay, so then, yeah, what we find is this is just the Fourier transform of the Weidmann function times kappa squared over 2e. And now we want to, from this, we want to get the number of axions per unit that produced per unit time in a space-time volume. Now, this is the probability for having one particle with precisely one momentum. And if you want to get to there, you have to count all the momenta in a given cell of the space-time. And this is something which is straightforward, but you have to sit down and be very careful. And I just tell you that this, when you count the so the in a finite volume you have discrete momenta, and so in a finite space-time, in a finite momentum space volume you have so and so many momenta. And if you count them right, you find that this is precisely the production rate, gamma k. And that means that this here, the gamma k that we are after, is given by kappa squared over 2e times Weidmann function, rho at k. Okay. Yeah, now come to what are the real-time correlation functions. So there's a whole bunch. I introduced this one Weidmann function. There's also the delta greater. So these are Weidmann functions. Delta greater AB of t is A of t times B of 0, and the delta less that we already introduced is the B of 0 A of t, opposite order here. And actually when this, we know here we discuss bosonic fields, and when you do this for fermions, one actually puts a minus sign here. So then this is plus or minus for bosons and fermions. Yeah, that's one set of functions, and well, these are basically all the others that you can consider can be built from that, and the others are, for example, the spectral function, which is rho AB is the expectation value of the, is it a factor 1/2? No, there's just there are two different. You have to, if you look into books or so or papers, you have to be a bit careful. There are two normalizations here. So I define it like this. And this is a commutator for bosons or anti-commutator for fermions. Okay, you can do more. I mean, like you can consider retarded correlation functions or advanced and whatnot. I don't have to write them all. I mean, these are the things we will use. And these are in fact all related, or these can all be obtained from our imaginary time correlation function, which we defined as A of minus I tau times B of 0 expectation value. Yeah, how can one see that? It's actually relatively easy to see if you look at this Weidmann function here. So let's here write this out more explicitly what this is. So delta greater AB of t is 1 over the partition function, and then the trace of e to the minus beta h. Then I have e to the plus I ht times a of 0, e to the minus I h of ht times b of 0. Okay, now you see from this expression that I can take this time here and make an analytic continuation into the complex time plane. So if this is my complex time plane, remember this thing here was defined on this contour here, so here's minus I beta, and so in the beginning this delta greater lives on the real axis. But now if I give the time here a negative imaginary part, this turns into plus a positive real number times the Hamiltonian, to which together with this here is still a negative number times the Hamiltonian. So if you take the trace and sum over all possible states, the states with the highest energy will be suppressed. So this will converge and this will exist. Okay? And here, this term becomes a negative number, a real number times the Hamiltonian. So if I would take the trace here, I would suppress the large energies. So the delta greater can be analytically continued into the lower, actually into the entire open strip here to the into the complex plane. And in particular, if on this part of the contour it equals our imaginary time thing. So there we have a relation, and now we can just Fourier transform back and forth, and then this gives us all these functions in terms of the delta AB. And to do that, one has to still use one thing. So we remember for imaginary time correlation function, we had defined the Fourier transform like this. That was integral from minus beta 0 to beta, d tau of e to the plus I on tau So that we defined only at this Matsubara frequencies, at the discrete Matsubara frequencies. But what you can show is that it can be analytically continued to the complex plane, and the only singularities you encounter are on the real axis, along the real axis. And remember, when we did this Matsubara sum, in a way we used it already, that we can, at least the propagator, we can analytically continue into the whole plane. So this can be continued into the complex omega plane, and only singularities on the real omega axis. Yeah, there you can get discontinuities, poles and whatnot, and then the one relation that we could use here is that the spectral density is given by 1 over I times the discontinuity of this analytic continuation here. So spectral function of omega, which is real here, is given by 1 over I times the discontinuity of this function continued, and then, oh no. So you go from above the real axis and subtract what you get from below the real axis, and the difference gives you, well, you take out the I and then you get a spectral function. And the Weidmann function that we would need here is then simply the spectral function times the Bose distribution. So delta less of AAB of omega is F Bose omega times rho AB omega. Okay, and this gives you the strategy to compute all these kind of objects. So what you can do is you can just start with the imaginary time path integral and then start computing, and then you should do the analytic continuation. And the important point when you do this is that you should first do all the Matsubara sums, and only after that you should do the analytic continuation. It has to do with uniqueness. I mean, there is no unique. I mean, so this is first as a function defined on this finite on a discrete set of points, and the question is, how is this unique to this analytic continuation? And the answer is yes, if there is a certain, I mean, if they don't grow faster than, I think they shouldn't grow faster than some power, some arbitrary, some power of frequency when you go to infinity. So this is the condition which makes this unique. And if you are not careful with with the Matsubara sums and the continuation, then you might find a continuation which doesn't satisfy this. So first do all the Matsubara frequency sums, and then you can continue. I should say that this is the real-time formalism to get, it's imaginary time formalism to get to real-time quantities. There are other approaches to real-time perturbation theory which never use imaginary times, real-time formalism. There are different flavors of it, and but it's a matter of taste to some extent. I prefer the imaginary time one because it's conceptually very simple. We do the computations precisely the way I already showed you, and then you have they depend on omega, and then we do the continuation. It's straightforward. The problem with this is a bit that it's not very intuitive. I mean, when you in imaginary time, you don't really see where the physical processes happen. So this is clearly a disadvantage, but okay. I think one can live with it. Yeah, so now I would like to show you what one would now do in this concrete example of the axion production. So what we have to compute is the two-point function of the rho. And let's see how this looks like.
Usually defined in the momentum space, right? After you pull out the exponential and so on. I'm just confused about your definition of the spectral function. It's usually defined in the momentum space, right? Hence spectral.
1 over what?
It's usually defined in the momentum space, right? The spectral function, and hence the name spectral.
Well, it's okay. Yeah, but okay, it's a Fourier transform then. I mean, that's.
Well, it's the difference between a Bose-Einstein factor and a Fourier transform of a Bose-Einstein factor. So, okay, I mean, fine.
Yeah, but I mean, you get precisely what you get. Yeah, yeah. Okay, so back to axion production. So we know how to do it in principle. So we need to compute delta AA, delta rho rho. And we have, so we have one row here which has two photon fields, and we have one here. And and the first thing you can do is you can just contract the one photon here with one there, and then same with the other. So one electromagnetic field, so you just get this diagram. So here is, say if this is at x, one is at 0, and here one is at x. And you can also view this as, I mean, if you think of the axion here still being here, that this is the axion, and here this is just the vertex you get from this interaction Lagrangian. Okay, now you can easily imagine what this process would correspond to if you do the Matsubara sum and then do the analytic continuation. The rate must be, I mean, it's just a kind of lowest order, the lowest interaction, and the rate, if you would just compute it for, say, from S matrix, then it would be the square of the amplitude of something, and which we see here could be from the square of this type of process, of this amplitude here. So this corresponds to this, and then you see that this is kinematically not possible. I mean, it would be like it, if you turn it around, it would be like the decay of an axion which is massless into two photons, which is not allowed. Okay, so this would be give 0. So we must include higher orders in perturbation theory here. And the next thing you can do is, let me draw this again. We may say add a loop, say a fermion loop here. And now, if you think of this in terms of a scattering process, this could correspond to this type of process here, where you have a fermion, and then which interacts with photon, and here two photons interact to make an axion. And this is kinematically allowed, and this would give you the leading contribution to the axion production rate. Okay, now if you look a bit closer and at this or this, then you see that if the momentum transfer here becomes very small, you have a propagator which becomes big. There are all massless particles here involved, and this gives actually rise to an infrared divergence. So this is the problem with this is integral. So if this is the exchanged momentum, which appears in our thermal field theory diagram here, if the integral is infrared divergent for small p. Oh, okay, we have seen infrared divergences before when we computed the pressure in the massless scalar field theory, and there we saw that if we include the hard thermal loops on the soft line, we get a thermal mass which then avoids this infrared singularities. Yeah, then the propagator never blow up. And here we can do something very similar. We have here a small momentum, much less than the temperature. And if we add, again, hard thermal loops, then we can, and we sum all of them, we get some finite result. Pressure of massless scalars, we can, or we have to, resum hard thermal loops on the soft propagator. Hard thermal loop, or into the propagator. So that means in this language here that instead of just a single insertion here, we include arbitrarily many of these bubbles. Yeah, so we resum this whole series and then we get one gets some good results. So this is, remember so I should be a bit more precise. So we assume that the momentum of the axion, so the momentum which goes into this loop, that this is hard. So K hard, meaning of order T. And we consider the region where this is soft. So P is soft. So P much less than T. And then clearly this momentum, which here is now P plus K, this is also hard. And that's why there are only these blobs on one of the lines, not on both. For the hard momenta, we don't have to do this resummation. Okay, so this is like similar to the scalar field case. It turns out that it's more complicated and well, maybe also more interesting, because the structure of the hard thermal loops in this case is different. Gauge theories is more complicated than for scalars. Remember, for the scalar, the hard thermal loop just gave a thermal mass. It's just like replacing the massless propagator by the one with the thermal mass gives you this resummation. So where the HT oil just give the thermal mass. I mean, the qualitative difference is that these blobs here, they have a non-trivial dependence on momentum. And not just that, they're even non-local. So, yeah. And we have a few minutes, so I could try to, I will try to show you how this works, how you get the hard thermal loop in this case. I will not be able to finish that. I will have to continue tomorrow. So the reason why I chose QED is simply because then if you had QCD, you had a lot more diagrams here. I mean, you have gluons and with different vertices. Also with QED, it's the hard thermal loop is for a photon field is just given by this diagram. So in QED, so how does it look like? We have, say, our photon momentum P here, and then some loop, and say loop momentum L and L plus P. Yeah, this, we start the calculation in the imaginary time formalism. So that means that we have an integral over the spatial momenta, but a sum over Matsubara frequencies. So we have, we have some, from each vertex we have an E, so we have E squared, and then we have some numbers, I don't know, 2 or whatnot, it doesn't matter, and then we have an integral sum over frequencies, and integral over spatial momenta L. And here we have now the fermion propagators. You know, massless fermion propagator is just proportional to 1 over L slash, which I write as L slash over L squared. So here we get, from this propagator we get an L squared, 1 over L squared, and from here we get a 1 over L plus P squared. And then we have some L's and P's in the numerator where we have to trace. So this comes with trace of, let me just call this T mu nu. So this has an index mu, this has an index nu, T mu nu of L, let's say, of L and P, and divided by L squared times L plus P squared. Now this is how you would compute this, and I gave you this as an exercise. So do you know what are the Matsubara frequencies for fermions? We said for bosons it's n times 2 pi times the temperature. N is any integer. So what is it for fermions? The difference is that for fermions, the propagator is anti-symmetric. Is anti-periodic, sorry. Anti-periodic. Yeah, right. It's 2n plus 1. Where now L naught here is I write it like this. The frequency is I times 2n plus 1 times t, pi t, sorry. Yeah, that's our loop integral, and now the next step is to do the Matsubara sum. Okay, and that was another exercise. So we have, if I have a sum of this type. Actually, when I do computations myself, to remind myself that this is fermionic, I put the tilde over the sum. So let's do that here too. And now we have some function of, say, I omega n. Okay, and one can actually do the same trick as before. One can find one finds a function which has poles at the locations of the Matsubara frequency, so they're now not at 0, but they're now like this. And the function which does the job is actually not the Bose distribution, but the Fermi distribution. So this can be written as an integral. So then we make this contour, we turn this contour here again into this contour, up and down, which is then the integral along this contour d omega over 2 d omega over 2 pi times I times, and for bosons we had here 1/2. Again, there's this somewhat arbitrary 1/2. And there was a plus f boson, now it's f minus f Fermi of omega times this function h of omega. Okay, and that we then have to apply to this function, and we move these branches of the contour to minus or plus infinity, and when this happens we hit some of the poles of this function, and we have to take into account these residues. And that we will continue tomorrow.